Today, I'm going to tell you about developing and testing TensorFlow Lite edge algorithms. This is going to be something that you can do without having any hardware. So normally, of course, people are afraid of hardware because it's hard, as they say. And to do anything with it, especially to do machine learning on it, you need to actually have it physically. Except that right now we're developing a framework. Actually, for some years, we've been developing a framework that allows you to do that without having anything physical, which is called Renode. A little bit about us quickly. We've been around for 10 years, and what we consistently have been doing is building open source platforms, open source products with our customers, for our customers. As it was mentioned, we do it for various branches of industry. We don't really kind of focus on the specific industry per se. We work with all sorts of high tech. And I think what's important to know about us is that we participate in a lot of organizations that drive the development of open source, including Linux Foundation, Zephyr Project, Chips Alliance, RISC-V, and Open Power. RISC-V especially will be mentioned quite a lot today because this is, a new and exciting open source hardware architecture that's enabling people to build, AI not only on the software level but also kind of influence and enrich hardware with AI capabilities. And what we like to do as part of our job is to kind of not only just build things. We don't just build like robots and drones and other things. We also help people innovate in terms of methodology and the way things are made. And we do that using open source. If you want to see what we do, there's a broad array of things that we do is visible on our website. There's a technical showcase that you can just open our main website and scroll down. You'll see all those topics popping up. There's a variety of different things. Most of them will actually just take you to, you'll read a note, but then that'll take you to GitHub. You'll be able to replicate our work because the majority of what we do is open source. And as I mentioned, we kind of deal with a variety of topics. It's both hardware, software, AI, FPGA, and ASIC stuff. But kind of perhaps most importantly, we build tools that kind of influence all those other topics. We help people innovate in terms of how they work, not only what they do. Moving on to TinyML as such, as we tend to say, TinyML is this kind of trickling down of machine learning capabilities into small devices. So in order to do machine learning in the past, you needed, of course, big and beefy computers and servers. This is no longer true so much. You've seen probably in your own, for example, mobile phones, you can do quite a lot of interesting AI capabilities. And this is going even further now. This is migrating into very small devices that we might embed in various little things. And those kind of devices, of course, they're much more omnipresent than, say, a server. They're much closer to you. They're much nearer to the end use case. And using machine learning on the very edge actually gives you some advantages. For example, you can use less power because you're not communicating with some kind of a cloud infrastructure. You have less complexity. Those devices can be fairly simple, but still deliver pretty interesting results. Also, machine learning in a small MCU could potentially give you much better latency in terms of the response time, as well as, of course, because you're not transmitting any data anywhere, you might get much better privacy measures than you would if you had to communicate all those data into the internet. So you can also look at how TinyML enables things to be more self-dependent, self-reliable, and it enables autonomy of devices that normally perhaps wouldn't be able to operate without the internet or without some kind of a connectivity. But now, given the fact that processing power is increasing, you can do much more locally. Suddenly, those devices become independent, and you can realize some specific functions without having to consult with the cloud. And all of these features enable some new use cases, and those use cases might be related to recognizing gestures, which of course requires quite a good latency. It might be recognizing your voice and reacting to it immediately without also compromising the privacy of what you're saying. It might be some kind of anomaly detection that's living very close to the device that's behaving anomalously. So overall, There's some new use cases. I've just listed a few, but of course there's other cases that are just popping up that we might even not understand today, but they're going to be made possible by trickling down of machine learning into those small devices. But of course, it's all pretty challenging as well, given the fact that these are constrained devices. They have power performance limits. They have less memory than a smartphone or a server. So of course, it kind of makes it not so easy to design, right? If you're designing a system that has TinyML in it, you're going to face a lot of constraints. The end system might be actually fairly simple and elegant, but the process of getting to that system might be quite hard. And especially testing is a difficult topic because, given the fact that you're probably working with systems that might comprise multiple devices, those devices might be of various kinds because they're adapted to a specific use case. They have various input and output capabilities. All of this becomes extremely hard to test in physical systems. You might have difficulty sourcing your hardware. You might especially have difficulty making scalable testing methodologies because physically connecting and checking various configurations of those physical devices is just going to be very hard for you to do. So basically, what people typically do is they rely on manual testing procedures, which get very tedious. Or they just don't test. Actually, that's what happens a lot, and we see that among a lot of our kind of customers that try to somehow make do with development without a lot of testing, and then they realize this doesn't make any sense. They have to somehow find a way to test, except manual testing is not really a great way. So, and also if you want to test physically, you can. We've seen our customers also build huge testing rigs of hundreds of devices where they can test things physically on real hardware. The problem is that you don't really get a lot of scalability. That's one thing, but also repeatability and determinism go out of the window. If you want to repeatedly test how a given sensor and processing device will react to a specific input, you won't be able to do it repeatedly in a real environment. Even if you kind of automate everything, you're still going to have variable results depending on what exactly happened in the physical world. And only kind of doing that in some kind of a simulation gives you the ability to really have repeatable results and deterministic results. And these challenges are actually pretty universal. The tools that we build help companies like Google, Microchip, Arm, QuickLogic to solve those issues, and all of these players, they've realized, okay, you can see there's a huge shift, there's a huge focus right now going on tiny machine learning. Facebook is also kind of going in that direction, and plenty of companies are looking at this world of small devices and thinking, how could we leverage those? How could we use those to enhance our services, to offer new services? And for example, Google and Arm are using Renode to test and develop TensorFlow Lite machine learning algorithms for small devices. QuickLogic, which is a semiconductor company building FPGA systems, has been relying on us to provide both Renode, the simulator that I'll talk about today, but also other open source tools and methodologies, including their FPGA fabric, which used jointly kind of can give you very interesting capabilities of developing machine learning applications, because you can use open source FPGA tooling to create machine learning acceleration inside the FPGA, which plays very nicely with this entire methodology. And Microchip, on the other hand, has been working with us for many years now, and they're developing this RISC-V based platforms. I mentioned RISC-V already, which are especially focused on AI applications and low power applications. And Renode is powering their entire pre-silicon development platform. We're having joint webinars and talks and very tight collaboration around enabling people build systems without actually physically having those systems. So there's quite a bunch of people working with us on this. Specifically, what I'm going to focus around today is Google and the collaboration we have with them around TensorFlow. The entire thing started around 2018. We've been doing quite a lot of projects around both open source ASIC design, FPGA, software, machine learning. But in this topic of TensorFlow Lite, we first just created a little proof of concept and run TF Lite on RISC-V in Renode, and presented that at the RISC-V Summit of 2018, jointly on a workshop with the creator of TensorFlow Lite, Pete Warden, TensorFlow Lite Micro, right? And the first integration with Zephyr came approximately at that time too, because Zephyr is a real-time operating system that we encourage people to use, and we use a lot ourselves. So kind of TensorFlow Lite Micro is a good complement of that system. It's a good application that you can run on top of Zephyr RTOS, and that has resulted in a lot of collaboration there too. And all of that collaboration eventually resulted in another proof of concept where we joined all those things together and created an end-to-end machine learning demo that eventually got onto the TensorFlow blog. You can take a look at this note there. And later this turned into collaboration where we're actually actively working with Google to introduce Renode as the primary testing system for TensorFlow Lite Micro, and help them to adopt a continuous integration-driven methodology for developing this. So it's a very nice story there. The blog note looks like this. It's kind of pretty long, but it also comes with some code that you can actually run. The demo includes a board that you can also buy yourself. It's a Digilent RT-A7 board. This little module here is also something you can buy for relatively little money. And thanks to the fact that we can simulate this sensor board and simulate the CPU that's running inside this FPGA, we can kind of end-to-end run something on hardware, but also kind of simulate it on a computer in exactly the same way. And that's what it's going to look like if you run it. Here's kind of turning Renode on, running some simulation scripts, and starting the simulation. And here you can see there's some virtual gestures, a circle gesture and a angle slope gesture that are being recognized 2 times. And I'll walk you through that application later on. But this is pretty simple to get going yourself. So you're welcome to try. The repository is there, and there's going to be links in the slides when I share them. So, okay, I've been talking about Renode a little bit. So what is this thing anyway? It's a framework. It's a tool that we've been building for quite a while now. We created in 2010, and it started as a response to internal needs. We just saw, developing those hardware systems is so hard. We should totally build something that helps us to do it. We looked around and saw, okay, there's nothing really there. We need to build something of our own. And we had been building it in private, and thinking, perhaps we might open source it someday. But it took us until 2015 to actually say, okay, you know what, we have to do it. We have to go open source with this. And we did that, which we considered was a great move, because in 2020, it's being used by quite a bunch of people and a number of, both big corps and startups and also universities. So for example, actually Poznan University of Technology is using it right now for a course as well. So I don't think we'd ever have, achieved what we have without doing this as an open source framework. Even though it's a great framework, I think it has a lot of merit, but making it open has really been a very important strategic decision here. So Renode is a simulation framework I've mentioned already. You can use it to develop complex software for IoT systems, but also you can kind of do exploration and research on it. The interesting thing about it is that it gets very easy with Renode to create some virtual hardware. And of course, we typically target existing platforms because, like having something that you can physically test as well is kind of a good idea. But there is nothing stopping you from building a system that wouldn't normally exist and testing stuff in a system like this and then deciding, okay, I am going to build that system now. And same goes for pre-silicon prototyping. There very often in this space, you have some kind of a device that is being developed and everyone knows more or less what it's going to look like and how it's going to work. But that there's like a 2-year interval before, between actually architecting a specific system on chip and putting it on the market. That's actually what happened with Microchip and their PolarFire SoC. So this pre-silicon prototyping is an important thing that we enable. And also, like, if you're still developing your silicon, you can actually kind of co-develop the hardware part and the software part using Renode. And all of those use cases kind of complement each other. So we love to say about our framework is that it's both like pre-silicon, it both enables you to experiment and architect your stuff and perhaps give it to your customers as an early access when the hardware doesn't exist yet. But even if the hardware already exists, we still kind of, Renode should be used, and that's what it's meant to be used, how it's meant to be used. It's meant to be used very well into the existence of a specific platform. We have a lot of different features. I'm not going to go through them in detail, but the important part is that it's a very plug-and-play system. So we build building blocks from which people can assemble their hardware systems, and we try to be as flexible and deterministic and agnostic as possible, which are not easy features to support. But I think that's what makes the framework really good. Is that given the fact that we have, for example, determinism, we can easily enable continuous integration scenarios. Given the fact that we're software agnostic, we can enable a lot of different use cases. We don't care about what kind of software people run inside Renode. I'm talking about TF Lite today, but you can run any other machine learning framework that will run on hardware like this. Like, I don't know, Facebook's Glow and other things would run in Renode too. And it's flexible. We want it to be flexible because that plays very well with the open source aspect. People use it to do stuff that we didn't really think was possible. And also worth noting is that it's a batteries included framework. So like we provide a lot of demos and binaries where when you download Renode, you're going to be able to run those demos without having to do anything. Like you're just going to have to type, one command, and you'll be able to run a bunch of demos that we just ship together with precompiled binaries, just so that it's easy to get started. And as I mentioned, it's like a multiple layer framework. You can kind of both build just system on chips, and that's how some people use Renode, with certain specific IOs and specific interfaces connected to your virtual CPU. But you can also build entire devices, and I think that's what makes it interesting in this machine learning context. You can do not just the CPU, but IOs, sensors, right, and input data into those sensors and run your entire stack, your entire application inside Renode. And then you can also go to a complex system, which would potentially enable you to do, multiple devices connected via networks and so on. And of course, we have all those peripheral capabilities. You can connect a thermometer, humidity meter, accelerometer, and so on. And that kind of enables us to work with synthetic data, but also potentially real data. I'll tell you about that in a second. We support a lot of platforms. I'm not going to go through this in detail. There's a lot of boards that just come with onboard support. You might recognize some of the boards you're working with, perhaps at university. And you can do a lot of things. I'll leave those links with you. I won't go through this in detail as well, but there's a lot of blog notes and use cases people are doing with Renode. I encourage you to read those. And of course, you can run Linux inside Renode. So this little penguin there running on a frame buffer, it's a virtual frame buffer running completely on a computer. This is our friend Drew, an ambassador of the RISC-V Foundation, who loves playing with Renode and doing crazy stuff. Okay, going to testing and metrics, which is kind of the focus of today. We envision Renode to be used in not only on the local PC aspect. Of course, you might start with running it on your local PC and perhaps collaborating with others because they'll have the ability to reproduce your work very easily with Renode. But what we look at is a company environment or a university environment, an environment where multiple people collaborate and try to, make something work. If you want to make something work, you need to have a testing suite that you can run continuously and track regressions. And we enable that, and that's the way we encourage people to use Renode. Of course, it's very normal in standard software, but in those kind of small devices and embedded systems, people don't typically do that much of that. They might, of course, compile the binary in CI, but they don't really test much because normally you'd have to connect those physical boards to a server in a server room. which doesn't really happen very often. Instead, you can run a simulator, and that's kind of what we want people to do. And what it looks like in the CI is you can take a look in our demo repository. There's a CI flow that performs the entire demo automatically. And of course, this is a demo of Travis, but you could run it with GitLab, Jenkins, GitHub Actions, and so on. The demo itself, I think it's interesting to look at because it contains a bunch of files that might explain to you how the framework works. The first file there is a C# file. This is a model of a peripheral, I2C in that case, that enables us to connect the relevant sensors. This particular model did not exist in Renode at that point, so but fear not, Renode makes it very easy to just create a little model of your peripheral, and the cool thing is you don't need to recompile Renode. You can just compile this on the fly. We're running the .NET platform, the C# programming language, so you can just compile this file on the fly, and you're going to get that interface in your LiteX platform easily. You don't necessarily need to dig into the internals of Renode to add something to it. Then there's data files, of course. To have repeatable results, you need to have data files. We can read that data from files. Then there's a REPL file. A REPL is a format that we created to describe physical hardware platforms. It's human readable, modular, and extendable. And so we can build platforms that have different peripherals on them without having to code. Again, to use Renode, you don't have to change Renode or code in Renode. You can just connect dots, and that's how you would do it. It's like a YAML-like format where you just specify what connects where on what address and what kind of features it has, what kind of IRQs exist in your system, and so on. So building a virtual system is pretty easy as long as we have the relevant components. If we don't, then you have to model them. But if we do, rearranging them on your platform is actually fairly simple. If you wanted to have, I don't know, double the memory than you have right now, this is just a single line change. So I think that kind of gives you a lot of flexibility to build your own platform as you want it, and then change your mind and change your platform very easily. Then there's a REST file. This is just a Renode script. So everything that you can interactively type in Renode can also be executed as a script. So that's just a script. Robot is a framework for testing that we're using. It's kind of a pretty cool framework in itself. I'm not going to go through it in detail right now, but as you can see, this amount of file enables you to simulate this entire platform and do an end-to-end test. If you want to test things, you also probably want to see how it performs. So we also have a built-in Renode metrics analyzer that gives you the ability to count how many instructions were executed, memory accesses, and so on. And this kind of data is very useful in CI because you can effectively track your progress over time, not only if you're breaking things, like if things completely stop working, or perhaps they get slower. Especially in machine learning, it could be very important. If you're implementing a different layout of your neural net, it might be that suddenly your stuff, you thought it would get faster, but it got slower instead. And we have virtual timestamps that we are capable of, so you can track your progress inside this virtual time world that we create so that the data will be deterministic. I think that's a very important feature. And one of the things that we also enable is, and this is kind of still in development, but pretty cool, is a set of testing pipelines where we're building and continuously testing a set of different platforms and different use cases in Renode and putting that online. So that's on testing.renode.io. And there you get a nice, not only just a dashboard, but also some results of the tests and logs and artifacts and so on. So how can you, kind of jump on board of this? Of course, you can join us and help us develop Renode, especially if you like C# or like building these kind of things. We encourage you to join. But you can also go and, for example, use it in your master's thesis. We've had a master's student that was experimenting with various CNN model architectures. And the cool thing about using Renode for this is that the code running on the devices did not have to be instrumented, and you could still get a lot more information that you normally would be able to do on hardware. And you could also see, what's going to happen if my device has more memory than it has now. without actually changing your board to some other board. So that's a very successful MSc we did. You can also try it out very quickly in Google Colab. If you don't know, Colab is a Jupyter notebook in the cloud. Like Google gives you servers where you can run your machine learning stuff. And now you can also run tiny machine learning stuff in the cloud. This all gets executed in the cloud, and you can see some graphs, which will show you how your thing performed. Yeah, so that's the link and some details about this. I'm going to skip this for now, perhaps, and get to the next thing. We also run Internship, paid internship program that kind of enables you to work with these kind of things. For example, one of the internships we had recently was in the area of speech recognition, and again, implementing some speech recognition scenario in hardware for a TF Lite Micro, a speech recognition demo. And also, we're running a course at Poznań University of Technology. This is like a Antmicro part course. They're using our methodology to develop things, Zephyr, Renode, Sphinx, TF Lite, Git, and GitLab. And it's a collaboration with ST. So overall, I'm very excited for this course, looking forward to how it unfolds. But of course, like, we're looking at how we can make those materials available, not just to the people taking this course this semester, but to anyone. And we even have interest from Harvard to get their students to do this kind of thing. So I'm pretty excited for this too. And quite simply, if you want to get started, just go to our website, to renode.io, and there's packages for various operating systems, and you can get going in 5 minutes. If you want to learn more, there's a talk, there's a keynote speech we'll be having that describes some of our collaboration with Google, Zephyr Project, and QuickLogic, entitled Building an Open Edge Machine Learning Ecosystem with RISC-V, Zephyr, TensorFlow Lite, Micro, and Renode. And that's going to happen in December. I think it's on the 8th. So we encourage you to join that talk. I'll be able to expand. Well, I mean, this is going to be a panel, and we're going to be discussing different things. But there's going to be quite a few new updates from today, because we have this project going on where we're developing this very actively. So I encourage you to join and see what changed since then. Okay, that's about it. Thank you. Questions?
Hello. Well, this is moderator speaking again. Well, you did not see me, actually, because in the meantime, my camera has crashed. Sorry for that. It's just a teeny device. Well, it also crashed my browser, but so I'm back, okay, and I'm fine. So thank you for a very nice presentation. It is really looks like a future of many areas of machine learning and applications of machine learning. And the audience has 2 questions. I will read them aloud for this streaming. The first one is: are there any limitations of TensorFlow Lite in the comparison to TensorFlow?
It's, well, first of all, is the resources you have, right? Like, certainly the devices are smaller. So there's like TensorFlow, there's TensorFlow Lite, and there's TensorFlow Lite Micro. TensorFlow Lite Micro is the stuff I was talking about mostly. That's the part that runs on microcontrollers. TensorFlow Lite will run on something like a mobile phone, for example. There are limitations in terms of compute. Also, I think it's important to note that TF Lite Micro is a bit of a different beast than the others. It's actually an interpreter. Actually, there's other people, including Arm, I think, that are working on making this also a compilable thing. And you know, due to memory constraints and other things, there's a certain amount of hoops you have to jump through to even do machine learning on these kind of small device, because we're talking microcontrollers, you know, 100 megahertz microcontrollers with a very limited amount of memory, like hundreds of kilobytes perhaps. But you can do surprisingly much. And so yes, there are limitations, of course, but that's the whole point. Because of the limitations, it's such an exciting field, because you have to figure out how to build these things without relying on, you know, 32 gigabytes of RAM and things like that, right?
Okay, thank you very much for your answer. And before I read the other one, there is a short follow-up question from myself. Do your framework support somehow migration from regular TensorFlow to this micro version? imagine that I have a project and I found, let's say, somewhere in a GitHub, a very interesting open source project that is that fits my master thesis or something like that, and I would like to run this on this micro platform. Should I start with some specific tools to scale down?
That's an excellent question, of course. So first up, yes, there exist methods to kind of shrink down, networks to fit them into these kind of devices. But I agree, this is sometimes a little bit idiosyncratic to specific devices and requires quite a bit of hand tuning. I don't think there exists something that just automatically, converts your network and there you have it. But we do have a master's thesis right now running with one of the students at Poznań University of Technology, where what we're looking at is a framework from, I think, MIT. It's called Once for All, that enables you to train networks for multiple platforms and applications at the same time. So that's exactly the kind of thing you're asking about. Can I, build something that's scalable between small and big devices? And it's the same thing. So there are already attempts to accomplish that, and we're researching that. There's an MSc where we're going to be trying to do exactly this. Of course, the framework itself already exists, and it's a very promising framework that we think is going to be great. But of course, we do want to see how it works in practice and whether it actually works as advertised, so to say.
Okay, thank you. So let's proceed to the next question. Are you actually seeing more people moving towards doing some ML on small devices rather than using the device as an interface to ML that happens in the cloud?
I mean, we're seeing more people moving to tiny devices, but of course, ML in the cloud was there always, and smaller devices as input data into the cloud, that has been going on for years now, right? So the interest is definitely growing, but I'm not saying that tiny machine learning will replace cloud. This would be not very clever to claim that. I think that it's just going to be a great complement. There's still going to be a lot of things that have to run in the cloud for various reasons, even just compute. But if you want to process like a sensor input, right? If you want to say whether something should happen because of a temperature change, should you really be going all the way to the cloud just to decide about that? I don't think that's really reasonable. It could be handled perfectly fine in the same room, perhaps, that the temperature is being read. It's not always viable. It doesn't always make sense, but I would say it should be the default, right? Your car should be able to drive itself autonomously without connecting to the cloud, because otherwise you could potentially crash if you lost connection. So, and even though it used to be impossible, and that's why people thought we're going to do everything in the cloud, right now this attitude is changing. So many things are becoming possible that people are saying, okay, it actually didn't make sense to send all that data into the cloud. We can do this locally in the device.
Okay, thank you for this very interesting discussion. We do not have any more questions, so thank you again. It's really nice to see this progress in application of machine learning in real life technology and things that perhaps we will have in our laundering machines in few years.
Yep. Okay, thank you very much.
Thanks again.
Cheers.